I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
Picking up some dust.
In the 1960s, an impossible dream came true when human beings walked on another world.
The Eagle has landed.
In all, 24 Americans went to the moon. But it took an unseen army of over 400,000 engineers and technicians to make it possible. This is the story of the men and women who built the machines that took us to the moon. In the early 1960s, as NASA began training astronauts to meet President Kennedy's challenge, it realized there was one key area of expertise it knew nothing about. Nobody knew how to build a spacesuit that would enable a human being to survive in the lethal lunar environment.
There was enough cartoons and little movie clips and stuff like that around that you had this excitement about space. But you had no clue. So it was something brand spanking new.
NASA was designing spaceships, you know, the Saturn, the Apollo, the lunar module, all these pieces of hard goods. They knew how to bolt metal together. They could do drawings. They understood that. But when it came to a spacesuit, you're talking fabrics. And when you try taking it from the world that knows hard goods, it became a real problem.
Joe Cosmo, a young science graduate, remembers being called by a puzzled NASA engineer.
He says, "We're wondering if you might be interested in working in some new areas that we're starting, life support and spacesuits, whatever they are." And that was his exact words, whatever they are. And he said, "Does that sound of interest to you?" Of course, I'm looking for a job, and I want to get in the space program. And I said, "Well, you know, my background is in propulsion and structures. I don't know much about spacesuits." His remark was, "Well, no one else does either, and we're all going to learn."
But learn from what? In the early years of what became known as the Apollo program, there was very little experience to draw on. The first man to wear the sort of suit the astronauts would need was U.S. aviation pioneer Wiley Post. In the 1930s, Post commissioned a flying suit for an attempt on the world altitude record.
They had taken a diving helmet from a diving suit, and because Wiley Post was blind in one eye, they had physically moved the optical viewport off to one side to make it easier for him to get the best possible visibility.
Post's suit enabled him to reach 50,000 feet, higher than the cruising altitude of a modern airliner. At this altitude, temperatures drop to minus 40 degrees Fahrenheit, and oxygen levels become dangerously low. Over the next 20 years, rocket planes took men even higher. To help them, a new generation of high-altitude suits were constructed.
The X-15 was basically a very compact, very slender, rocket-looking type aircraft that was carried to high altitude under the wing of a B-52. and since it used rockets rather than jet engines for propulsion, was capable of not only high altitude and speed records, but was also capable of suborbital spaceflight.
It was followed in 1959 by America's first space program. Mercury put man into orbit around the Earth. But in all these craft, the cockpit provided the first line of safety. The flying suits were only there in case there was an accident. Kennedy's plan to have men leave this safety and step out onto the moon would demand something much more sophisticated. To illustrate the challenge, NASA introduced the U.S. public to a new cartoon figure, Andy Astronaut.
If Andy were to step out on the surface of the moon without a spacesuit, this is what would happen. In the near vacuum of space, the gases within his body would immediately expand. His blood would appear to boil from the rapid expansion of gases coming out of solution in his bloodstream. Andy would soon feel the effects of another condition of space, lack of oxygen. After 20 seconds in a vacuum and without oxygen, Andy would be trading in his astronaut wings for a more permanent variety.
The problem was to build a spacesuit that could be pumped full of air to compensate for the lack of atmosphere, but also remained supple and flexible. Early prototype pressure suits were almost rigid.
A suit is like a balloon. You know, if you're going to have 3.5 psi inside it and vacuum outside it, then something has to keep all that air in. So think of the suit as a balloon. And if you have a cylinder, which is what we made, it's very difficult to bend it.
NASA realized it needed to draw on new areas of expertise. And in 1962, tenders were invited from U.S. industry to build the first Apollo spacesuit. 8 companies submitted proposals. Most were well-known names in the aerospace industry, but one was not. The International Latex Corporation was best known for its Playtex bras and girdles. The company was the rank outsider, but it had one big advantage. It didn't know much about space, but it knew more than any of its competitors about making flexible rubber clothes that moved with the human body.
We had a lot of experience with dipping rubber products such as ladies' bras and girdles and things of that nature, so we knew we might have a good in with building a great suit.
The company's prototype was based on a series of flexible rubber joints.
The elbows and the joints all flex because of this system right here. It was a convolute. And a convolute is really nothing more than a rubber dip part that has all these little ridges to it. It allows the air to compress on either side and move about so that you weren't fighting against a pressurized cylinder. So where your elbow flexes and your knee flexes and your ankle flexes, this allows that to flex back and forth. In addition, it has these metal cables right here, and these take the load of the suit because when the suit's under pressure, it's under tremendous load, and you don't want those legs growing any longer, the arms growing any longer. So all the strength within that suit because of the pressure has to go through these metal cables right here on either side. And they also act as a hinge because as this suit's flexing and walking about on the surface or you're bending your elbow, these cables right here allow it to flex back and forth.
It was simple and obvious, But nobody else had anything quite like it. And in April 1962, NASA took a gamble and awarded ILC, as the company became known, the contract to build the Apollo spacesuit. But there was a catch. ILC knew all about rubber clothing, but had almost no experience of handling major government contracts. So NASA appointed another company to oversee the whole operation. Hamilton Standard was an established engineering facility that had originally pitched for the whole contract. The company's engineers were surprised and delighted to have a role in the program.
When I told my girlfriend I was going to go work on putting a man on the moon, she asked me what I had been drinking, was I sure I was sane, and a few other things like that.
But the wedding between Hamilton and ILC was a marriage between two very different companies and would, in the years to come, cause NASA deep concern. By summer 1962, the cracks in the arranged marriage between ILC and Hamilton Standard were beginning to show. Tom Harala worked for Hamilton Standard.
We were making propellers for both commercial aircraft and also for the Department of Defense. International Latex at that time made brassieres. We had two totally different personalities.
His opposite number at ILC was Homer Ream.
There was always this skepticism of Hamilton Standard's appreciation for our technology and our concern for Hamilton Standard, not thinking that consumer products people are capable of doing this job.
This was a very interesting relationship because both organizations thought they should be the ones leading the challenge, and it was described by many as a shotgun marriage.
But despite the obvious rivalries, in the early months, nobody wanted to dwell on the problems. NASA was demanding results. At ILC, the first suits were turned from prototypes into production models.
Our industry was fortunate because a lot of the people that had worked in Playtex were very good with sewing. They could sew ladies' products together. So we took a lot of those talented sewers and brought them over to the spacesuit line.
I was sewing baby pants, and then an engineer came to me and asked me if I would mind trying something else. And I said no. But I never thought in my wildest dreams that I would be making spacesuits.
It demanded greater care and attention than anybody at the factory had ever experienced before.
It was critical that these seams were sewn to within about a 32nd of an inch, which is just about smaller than a pin. And these tolerances had to work every time. They had to be perfect.
Everything was inspected. They had to count those stitches and make sure we didn't have less or more in every inch.
The sewing machines were just walking very slowly, stitch by stitch, to make these suits, to put them together.
One of the hazards was sewing pins. Even a single one left in a suit by mistake could cause a fatal accident in space. Eleanor Foraker was expected to keep track of them. She gave each seamstress different colored pins so she could trace who had done what.
I was walking by an inspection table one day, and I saw a pin. It had a red head on it. So I checked the paperwork, and I found out who did that. And I went to the lady, and I asked her, and she just kept looking at me and said, I didn't do it. I said, well, I'll tell you what, here's your pin. And I jabbed her in the behind with it.
Meanwhile, at Hamilton Standard, engineers were facing a different set of challenges. Their job, as well as supervising the contract, was to build the life support system, the backpack that provided the astronaut with oxygen and kept the spacesuit pressurized at a comfortable temperature. They called it an environmental control system. It was Earl Ball's job to design it.
Nobody had ever done this before. We were going to make effectively a little space vehicle with a suit and this environmental control system.
One of the challenges was to provide the maximum oxygen for the minimum weight. To do this, Ball used what's known as a rebreathing system.
Now, normally when you breathe, you exhale oxygen and CO2, and that is just blown away, and you waste all that oxygen that you've just exhaled.
Hamilton's system removed the carbon dioxide from the exhaled oxygen by passing it through lithium hydroxide. It meant the same oxygen could be used over and over again. It was at least 20% more efficient than a traditional aqualung. Hamilton, in its capacity as environmental control experts, was also responsible for what was delicately referred to as waste management. Don Rethke became known as Dr. Flush for his ingenuity in dealing with the issue.
There was no bathroom, as you and I know it. There was no cosmic commode. And their training was not that good to hold it for several days. So they needed some degree of body hygiene, if you want to call it.
Don always was able to put humor behind the work that he was doing, and many times it was appropriate because he got pretty crappy jobs to deal with.
This is the pee pouch and this is the poo pouch, okay? Don't get the two confused, because the wrong pouch will not work on the right place. So inside the urine collection assembly, which we kind of affectionately call the pee pouch, was about a 1 liter bag in the area down here. And the attachment to the body was done by a condom with a hose on the end of it, which you can urinate right into the bag.
The condoms initially came in 3 different sizes: small, medium, and large. But few astronauts, whatever their real dimensions, were willing to accept they were anything but large. So NASA changed the categories.
We changed the name to large, gigantic, and humongous. So large still works.
Gradually, piece by piece, the life support system came together. What nobody realized as they started to test the suit was that there was a potentially lethal flaw. In 1963, as NASA put the Apollo spacesuit through its paces, they discovered they had a problem. Everybody had assumed that cool air pumped into the suit from the backpack would be sufficient to regulate the temperature. But as astronauts now started to use the suits, they were becoming dangerously overheated. NASA panicked.
In October of 1963, NASA gave Hamilton a 2-week ultimatum to demonstrate a solution to the astronaut cooling problem.
The whole program is in jeopardy. There was a threat that we would lose our contract if we didn't measure up to NASA's requirements.
Unfortunately, that wasn't as easy as people expected.
Dave Jennings was charged with finding a solution in record time. He was shown designs of a British garment which used water-filled plastic tubes. Jennings set up an experiment to see how well it worked. Harlan Brosey was his test subject.
We wrapped his arms and legs in PVC tubing.
We then put a sweatsuit across my body. Then, in addition, to make sure that we didn't evaporate anything off of the sweatsuit, we put a plastic suit over me, plastic boots, plastic gloves, plastic all over, so that no water could possibly get away from the body. Including my head, I believe, was covered with a plastic bonnet.
The idea was to ensure that none of Brosey's body heat could escape. Then the PVC tubes were hooked up to a bucket of iced water.
Well, when they turned on the cooling, it was just like jumping into Lake Superior. Man alive, was that cold. And then the treadmill wasn't running yet. I said, turn on the treadmill. Let's get warmed up a little bit.
And the treadmill was slanted at different elevations to make him produce the kind of effort he would if he was climbing a steep hill and walking fast, doing a great deal of exercise.
The cooling effect was very comfortable. I don't recall cold spots or hot spots.
The system worked well, and NASA charged Hamilton with building a water-cooled undergarment.
The cool water flowed into the connector and through the tubing to be circulated around the user's body.
There were hundreds of feet of fine tubing running over the entire body. Hamilton's system would become the standard method of keeping astronauts cool in space.
That was very good.
By early 1964, ILC and Hamilton were sending a stream of completed suits to NASA in Houston. Tom Harala was entrusted with their delivery.
And I drove it to my hotel, and then I had to take it out of my car and I had to bring it into my room and keep it in my room overnight to make sure that no one could tamper with it, steal it, or whatever it was, because it was classified confidential. It was also worth probably a pretty penny. So yeah, the first suit I delivered to NASA, I slept with it. It wasn't very enjoyable either.
Almost immediately, NASA began to reject them.
They were bulky, they were tough to move around in, they were tough to wear, they were heavy, and so the customer wasn't very happy about them. They expected to see much more progress.
One of the tests was in an aircraft that was used to simulate lunar gravity. You had to be able to fall on your back like a turtle and then successfully get back up without any assistance. Unfortunately, the new design spacesuit wasn't able to do that.
There are laws of physics that say you can't do certain things.
As the difficulties mounted, the long-suppressed differences between Hamilton and ILC bubbled to the surface.
Hamilton Standard would come down to our facility and try to tell us how to build suits, and they thought they were helping us, but there was more turmoil involved in this process than needed to be.
Our companies had totally different types of personalities in terms of how we dealt with products and how we dealt with the paperwork that supported the product.
Here we are trying to build a suit that the industry would find acceptable, and it just wasn't working. It was a very poor marriage, and it just didn't work.
2 years into the Apollo contract, the development basically reached a crisis stage. There was no more time. NASA was planning to fly the first Apollo flights in 1966, and the Apollo spacesuit was simply not ready to support that.
In autumn 1964, NASA despaired of the suit ever meeting its test standards and took the enormous step of canceling the contract. The Apollo program was without a working spacesuit, or even anybody to build it. In spring 1965, NASA relaunched the Apollo spacesuit program. For some years, it had been hedging its bets and also investigating so-called hard suits. Many were like medieval suits of armor. Yet, try as they might, the designers of these remarkable garments couldn't reduce their bulk. And NASA once more solicited proposals for a soft suit. Once again, Hamilton Standard submitted a design. So did ILC. The two old partners were now in competition.
We only had 6 weeks to develop this suit and put it into the competition, which was quite a challenge. So we had engineers working around the clock. They were breaking into rooms to try to get parts they needed because they'd be there 2 in the morning trying to put the suit together.
It was a frightening time in the factory. The only thing that kept it from being desperation, I would guess, was our dream that we would be successful.
The hard work paid off. ILC, free at last to follow its instincts as a clothing manufacturer, came up with a new, flexible, and close-fitting suit that was better than any of the competition.
We ended up winning the competition because our suit had great flexibility. It was built the way we wanted to build it. It had great narrow shoulders. You can look at the pictures and see how tapered this suit was compared to the other 2 suits.
The administrative difference was that ILC was now contracted directly to NASA. Hamilton was awarded a separate contract to continue building the life support system. The 2 companies were equals, and NASA would keep the peace between them. The suit now consisted of 3 separate garments. The water-cooled layer, an extraordinarily clever pressurized inner suit with flexible joints, and a white outer garment finished in a toughened nylon fabric that provided protection from the extremes of temperature in space. These can vary from minus 300 degrees Fahrenheit in the shade to plus 300 degrees in direct sunlight. The lunar boot had a large flat sole to prevent the astronauts from sinking into the soft lunar surface. The helmet had a series of sun visors to protect the astronauts from solar glare. And then there was the glove, probably the most complex and troublesome piece of the entire garment.
You wanted a glove that could pick up a dime but stop a bullet, and it was very difficult to do at the time.
After various permutations, the outside was eventually made from a brand new material called Chromel R.
And it was actually woven chromium steel, and it was woven into a material that would flex like a fabric, and we used that all around the gauntlet of the glove, which is the part that wraps around the main part of the hand. And this material was $2,000 a yard, which was phenomenal at that time. So it was a very unique material developed just for the spacesuit.
It was a nightmare for the seamstresses to work with, but gradually the new suits took shape. As the suits rolled off the production line, they were exhaustively tested. The company's guinea pig was Tom Sylvester.
I ran, I kicked and punted and passed and did a rolling block like they do in football.
From the rigid bladder of just 5 years before, the suit had come a very long way. It was still pumped full of air like a balloon, but it moved like a normal suit of clothing. To test the suit in reduced gravity, NASA turned the world on its side.
They would take the suit and suspend it in this crazy contraption where they suspended the astronauts or test subjects in the suit, and they would walk along this wall with this rig.
Dave Jennings tried it out.
I had free use of my legs, both legs, independently. I could jump and bounce around, and just like the pictures of the actual astronauts on the actual moon. Exactly. I did the same thing, big leaps and bounds. I found out that I could do somersaults, and I found out I could do backward somersaults, which is something that I always wanted to be able to do. These backward somersaults were so much fun that I did a dozen of them. And here were all these engineers standing around watching me, with their mouths open, I suppose.
But the ultimate and most dangerous test was a huge, specially constructed vacuum chamber.
They were able to pull all the air out to create a big vacuum, just like it would be on the moon. That way we could test our suits to make sure there was no leakage.
One such test narrowly avoided disaster. Jim LeBlanc was the test subject in the vacuum chamber. Cliff Hess, the supervising engineer outside.
Jim, while you're exercising, I'd like you to stay intermediate all the time, okay?
I'm pretty cool right now.
Okay, well, you'll warm up here in a minute, so let's stay right here if you can stand it.
The testing started just normally, like they all do. And Jim was at a vacuum in the spacesuit.
Well, I feel pretty good here.
With all the air sucked out, all that protected him was his pressurized suit. Then something happened.
I heard over the headset that he was losing suit pressure.
The tube pressurizing his suit had become disconnected. He was in serious danger.
There really wasn't any feeling. It was just happening so fast, trying to get the chamber back to a safe pressure and Jim to a safe pressure was inside the suit.
As I stumbled backwards, I could feel the saliva on my tongue starting to bubble just before I went unconscious. And that's kind of the last thing I remember.
Essentially, he had no pressure on the outside of his body, and that's a very unusual case to get, and there's very little in the medical literature as to what happens when you have that. There's a lot of conjecture, that your fluids will boil.
Within 25 seconds, a co-worker sitting in a partially pressurized antechamber and wearing an oxygen mask was able to dash in. At the normal rate of repressurization, it would have taken 30 minutes to make the chamber safe. Hess repressurized it in just over a minute.
That's much, much faster than you would ever come down in an airplane. It would really hurt your ears if you did that.
Finally, it was safe to let a doctor in. Miraculously, LeBlanc had already regained consciousness.
When I stood up in the chamber, I felt fine. My ears ached a little bit from the course of rapid repressurization, and that's basically the only effect I had.
This was one of the few instances where anybody was ever exposed to that low of a pressure and lived to tell about it with no obvious damage.
Such an accident in space would have been fatal. But thanks to testing like this, no astronaut has ever had to face a similar situation. The suits were holding up to everything that could be thrown at them, and the program was back on schedule. On January 27, 1967, the Apollo 1 command module caught fire during a practice countdown.
I got a call from one of my people in Houston, and he goes, "You probably didn't hear, but they had a catastrophic fire at the Kennedy Center."
All 3 crew members died in the intense heat of the blaze.
That was quite a shock. I almost had to pull over to the side of the road, catch my breath, because I thought, well, this is the end of our future.
The program started to just churn. Churn and churn and churn.
NASA demanded that all inflammable material be removed from the outside of the suit. But what to replace it with?
I felt as though this was going to probably be the biggest of all the challenges yet. And then when we got into it, it proved me to be right in spades. It was bigger than any challenge we had gotten into.
The company scoured the country, talking to manufacturers working at the cutting edge of fabric technology. They needed something that was tough, flexible, and non-flammable.
We had to take research-type materials and convert them into materials you could use and then put them in a spacesuit. It was a horrendous effort by a lot of people.
Rheem eventually tracked down a brand new material called beta cloth.
It was a woven fiberglass that was actually coated with Teflon before it was woven together to form this outer layer of the suit that protected against temperatures up to about 1,200 degrees Fahrenheit.
It was completely non-flammable and offered protection from temperatures way above anything ever likely to be encountered, even in an emergency. NASA was satisfied. Apollo missions 7, 8, 9, and 10 took men into space without a hitch. Then came July 1969, and the biggest test of all.
Okay, Neil, we can see you coming down the ladder now. Yeah, I'm going to step off the limb now.
As the Apollo 11 astronauts stepped out on the moon, the world celebrated. But for those who had built the suits, the moonwalk was several hours of pure anxiety.
As Neil Armstrong came down the ladder and they started doing their things on the moon, I had a smile on my face, but in my stomach were all these butterflies.
We've worked hard for about 8 or 9 years to make this happen, and when you actually see it happening, one side of your mind is saying, is this real? The other side is, wow, this is great. I just hope he doesn't fall over.
When the astronauts started jumping up and down, we were concerned that the pressure garment underneath of the outer layer could come up with a small leak or something like that. And we didn't want any accidents.
Every time they stumbled or tripped or fell, it was kind of like a little white knuckle grab and gulp a little bit.
The astronauts were obviously euphorically enjoying what they were doing and seemed to be ad-libbing a little bit of activity as they were going on. And every time this ad-libbing would come up, I could think of nothing but, please go back up that ladder and get back into the safety of that lunar module. All I could think of was the world is looking at ILC right now, and we need to get this over with.
It was 2.5 hours before the Apollo 11 astronauts finally returned to the lunar module.
When he went back up the ladder and shut that door, that was the happiest moment of my life. It wasn't until quite a while later that I reveled over the accomplishment.
I had tears rolling down my cheeks. I mean, I was just crying in happiness because all that work that we'd done, all those chores that we'd done and everything like that.
The suit and backpack had done everything expected of them, and in the years to come, enabled man to walk, run, jump, and work on the moon without a single significant failure.
It's a football-sized rock. It's a great Scott size.
It was the culmination of a long time, and it was very, very satisfying. It's the best thing we've ever done.
But this two-legged thing is great. Man, I can cover ground like a kangaroo. How'd you like that? Beautiful maneuver there, Charlie. What do you do for an encore? It's the old boulder rolling trick. Don't hit the rover. By golly. Think you've got a lot of it on you, too. No, that's okay. Hey, John, this is perfect with the limb and the rover and you and the old flag. Come on out here and give me a salute.